Go. All right. Well, welcome everyone. Thanks for being here. I'll be doing my practice for my defense, my thesis, which is titled Argumentation Quality from General Principles to Healthcare Applications. So as you all know, my supervisors are Serena and Elena, and let's just get on it. So first, I would like to talk about what we're going to be seeing in this presentation. I will start with the motivation. I will introduce some of the key aspects that we will be touching, mainly argumentation and argumentation quality. Then I will go further with my first contribution in this thesis, which is focused on argumentation quality assessment. To then go deeper into the medical domain, into the healthcare domain, to be able to integrate this argumentation quality and assess external knowledge in medical text. Finally, then I will show some demo systems that I have prepared, and finally I will conclude with all the contributions. So let's start with the motivation. First, in order to understand what is argumentation mining, and what is argumentation quality, let me show you an example of an argument. So let's say we have this quick example that says we should definitely switch to electric cars. Sure, the initial cost is high, but the long-term environmental benefits are invaluable. Besides, they are far cheaper to maintain in the long run. So this is a nice short argument for electric cars. And what we typically do in what is called the argumentation mining task is first segment this argument into smaller units, what we call argumentative discourse units. Like we have here, like for example, we should definitely switch to electric cars is a first unit. We label it as 0, and then so on and so on. We have sure the initial cost is high as 1, but the long-term environmental benefits are invaluable as 2, and so on. So after we identify the different components that we can find, the different units that we can find in the arguments, what we typically do is first identify the main claim that the author is making. In this case, is that we should all switch to electric cars. But there are other roles that can be taken into these units. Like, for example, if we go to the initial cost is high, we see a role of anticipating a counter-argument. So it's very typical that in argumentation, one anticipates an attack that it's going to receive, and then it will rebut it. So there is another role, it's called rebutting the counter-argument. As we can see here, that is saying that, okay, it's high, but the long-term environmental benefits are invaluable. Finally, there is another role that is to support the main claim, like saying here that besides, they're far cheaper to maintain in the long run. So we see that there are different type of roles and different type of components. And we basically, what we do in argumentation mining is assign them this label. So we have that the 0 is the main claim, the 1 is the counter-argument, the second is the rebuttal, and the third is a support. But this also shows us that there are relations between all of these components, and where, for example, the counter-argument, the one labeled with the 1, is attacking 0. So we have a relationship of attack. And then we have the rebuttal, so the second unit, which is undercutting the counter-argument attack. So in a way, it's attacking the attack, it's refuting the attack. Finally, we have another possible relationship, which is the support. So we have, as we said, that the last argument is supporting the main claim. All of this can be converted into a pretty nice overall structural representation of the argument. So what we typically call argument graph, where we have basically the main claim 0, we should definitely switch to electric cars, and all of the other claims with its own relationships, so support, attack, or refute. So now that we know how arguments are composed and the different roles in it and how we work with them in argumentation mining, let's talk a bit about argumentation quality. So as you know, arguments can be found in different domains, and they are not equally cohesive, equally persuasive, or equally good in terms of quality. So the question arises, how can we evaluate this? So going to another example, here we have a claim that says that everyone has an inalienable human right to life, even those that commit murder. So sentencing a person to death and executing them violates that right. The thing with this argument is that it seems cogent, it seems reasonable, it's making a sound argument on why we shouldn't have the death penalty. But it may not be the perfect argument for some people. For example, some of you may be closer to a case where a person was murdered, so you are not feeling, let's say, you're not being persuaded by this kind of argument. Or you could also think that this is not a fair or a relevant argument to make in the debate of death penalty. So this shows us that for argumentation quality, there are different problems and different things that we have to take into account. That, for example, first, that quality is not being evaluated as a single metric, but across different granularities. We have different aspects that we have to evaluate, like, such as relevancy, structural, rhetorical, and so on, that we will see later on. Also, many of these quality dimensions are subjective, so it depends on the person that is hearing this argument. It depends on the opinions and the preconceived opinions that they have. And finally, that if we wanted to propose an overall quality assessment, we have to address the complex interactions between all of these different dimensions, making it a very difficult task. So the main motivation for this thesis is that, okay, as you know, arguments, and as I said before, arguments can be found everywhere, and it can become a critical element in domains like, for example, law, politics, such as political debate, medicine, and education. And as I said, not all of these arguments are equally persuasive or logical coherent, so we may need a way to be able to distinguish between them. More so, nowadays, we have all of these generative AI systems that allow us to actually generate arguments, but we don't have a way to be able to assess the quality of them. So this arises a need to have a way to assess not only assess the quality of the arguments, but to assess large volumes of them, since well, the generation it can be infinite, let's say. So what we want to see is if we can first propose a way to model these multidimensional notions of quality to capture the key quality aspects, which is the first research question of the thesis. Then we want to explore if we can integrate the textual features, meaning the text that we can find in the arguments, with other features such as graph embeddings and emotion detection to improve the assessment of these argumentation quality dimensions. As I said, we also delve into the medical domain. So we would like to see what kind of adaptations are required to be able to assess clinical argumentation. Clinical text or medical text are not in the same, are not structurally the same, and are not addressed to the same audience. So we may need different kind of adaptations to be able to assess the quality of this domain. And finally, how can we integrate external knowledge to be able to enrich this analysis of in the clinical decision making and in assessing the explanations. So let's start with the first part, the argumentation quality part. In this section, we will address the first two research questions. So how can we model these notions of quality, and if we can integrate extra features apart from the textual ones to improve the assessment. So I will quickly address argumentation quality in the literature. There are different works that tackle different related problems to quality, such as argument relevancy, to detect convincing arguments, or maybe some kind of overall quality and assessment of the clarity, organization, and the strength. I have to say all of this work is based only on textual features. But more importantly, I would like to highlight the work of Washmuth in 2017, where they derive a taxonomy for argumentation quality. They take all the work from philosophy and psychology and social sciences, and they adopt the 15 most widely accepted quality dimensions. This is important because, as we said, it can be subjective, so we need a point in common to be able to discuss. And the main quality dimensions that they define are cogency, effectiveness, and reasonableness. This takes me to the quality attributes that we decide. So we go along this taxonomy, and we decide in this thesis to address a computational model for cogency, reasonableness, and what we call argumentation rhetoric. So let's see each one of them with a quick example to understand what they're talking about. So cogency focuses on the quality assessment of the arguments, where we assess the acceptability, the relevance, and the sufficiency of the components in an argument. So in this argument, I will go quickly through it, but it says it refers to a change of the law of the speed limit in the highways. So they put it from 70 to 55 miles per hour, and this is a comment from a website where a user is complaining about this, basically. And he's saying, okay, yes, this law saves lives with this new limit, but surely there are more cost-efficient ways of saving lives. For example, equipping every house with a smoke detector or putting more dialysis machines in hospitals. The problem with this is that all of these claims are not really relevant to what we're discussing. We are discussing about the change of speed limits in the highways, and it may be coherent. It may be in a way, it may be factual that putting more smoke detectors can help saving lives, but it's not relevant to the topic that we're talking. So it's not a cogent argument. However, let's see example 2, where we say that Sam argues that a balanced diet is essential for good health. He points at a study that shows people who eat a balanced diet are 30% less likely to develop chronic diseases. Some may argue that genetics play a bigger role, but the study controlled for genetic factors and still found a significant difference. So in this example is the other side of the coin. Here, all of the points that Sam is making are factual, we can check them actually because he's referring to statistics, to studies, and is even anticipating counter-arguments and refuting it. So we can say that it's sufficient to draw a conclusion. So it's an argument with a good cogency. Now going to the next quality attribute, the reasonableness. Here what we evaluate is the presence of counter-arguments. So as we discussed, a good argument should anticipate counter-arguments, and the rebuttals that the writer is making. So we have seen examples of this already, but I have another one here where Jane argues that working from home can increase productivity. She noticed that her colleague Tom, who works from home, always meets the deadlines ahead of time. And some may say that working from home can be filled with distractions, but it seems unlikely given Tom's consistent performance. So here, as I said, it's anticipating a counter-argument. It's saying, okay, some may say that you will distract it at home, but it's refuting it by saying that Tom's has a consistent performance and is having an increased productivity. Finally, the last dimension, the last quality attribute that we want to characterize is the argumentation rhetoric. So for argumentation rhetoric, we refer to the rhetorical strategy that is being used in the argument, and we characterize them among logos, ethos, and pathos. So logos refers to when one appeals to logic, to studies, to statistics, in order to convince the author, so the reader. So in this example, we have, according to a recent study published in the Journal of Medicine, individuals who exercise for at least 30 minutes a day are 40% less likely to develop heart disease. So it's referring to a renowned journal of medicine, is providing the statistics, providing all this information, is appealing to the logical sense of the reader. Then we have the ethos, which basically is a strategy where it appeals to the authority or the experience of the person that's making the argument. So here is saying, for example, as a cardiovascular surgeon with over 20 years of experience, I can confidently say that a balanced diet and regular exercise are the cornerstones of heart health. So as I said, it's appealing to the experience. He's saying, I am a cardiovascular surgeon with over 20 years of experience. So basically, it conditions you to believe the person, given the experience that he has. Finally, the pathos is also known as appealing to emotion. So this is, I think, the easiest one to understand. But here we have an example saying, imagine a world where your children can grow up without the looming threat of climate change, where they can breathe fresh air and enjoy the beauty of nature. So it's appealing to the emotions of your children growing up in a nice environment with fresh air, but also it's appealing to the urgency of the climate change and the problems that it may come with it, and so on. So to start showing my contribution in this work, First, we defined the annotation guidelines, so it's a good resource on how to annotate the different quality attributes. Then we annotate, actually, we propose a new quality annotated data set, which, by the way, very few of them exist, so it's a very interesting resource. And then finally, we propose a way to automatically assess these quality aspects in different persuasive essays. So you may be wondering how we annotated these different quality attributes. I will go quickly through each one of them, starting with cogency. In order to do this, we went to the social studies by Paul Stapleton and Yaming Wu, where basically they assess the quality of arguments in students' persuasive writing. They see how professors actually assess the writing of their students. And they come up with a nice rubric score that can identify the cogency for each argument proposed. So the rubric scores goes from 25 to 0, being 25 the highest score, so being the best cogency, and score 0 the lower score. So just to give you an example, a good cogency, a good cogent argument, the one with score 25, will provide multiple reasons for the claims, and all of the reasons are sound, acceptable, and free of irrelevancies. So as you can see, it's tackling the definition of cogency that we defined before. And if we go to the other side, to score 0, we can see that no reasons are provided. So you're making a claim with no premises supporting your claim, or none of the reasons that you are proposing are relevant to support your claims. And in this quick example, this is taken from our data set. If we wanted to assess the cogency of claim B, we will see quickly that first it's being supported by 3 premises, premise C, D, and E. And if you read carefully the text, you will see that all of the reasons are sound, acceptable, and relevant to the claim. So this falls under the definition of score 25. Then for reasonableness, we refer to the same study, and they also provide a very interesting table where they analyze 2 things. First, the information provided in the counterargument. So remember, we want to assess the existence of counterarguments and if it's being refuted or not. So first, it assesses the counterargument proposed in the argument, and then it assesses if there is a rebuttal, and more so if the rebuttal actually refutes or points out all of the weaknesses that the counterarguments are provided. The definition is very similar to the previous one. We have a score 25 to score 0, being the score 25 the better one, and score 0 the worst. And in this example, we can see it quickly. We have a claim C that is being attacked by claim E, so we have a counterargument that's being introduced. And we have then claim F supported by premise I that is refuting this claim E. So if we go to the table, we will see that as per the counterargument claim E doesn't have any premise supporting it, so automatically will fall under the score 0. So you can see here, no reasons are provided for the counterargument claims, so automatically gets a score of 0. But for the rebuttal, we see that if you read carefully the text, you will see that it actually points out all of the weaknesses of the counterargument with a superior reasoning quality, therefore falling under the definition of score 25. So we annotate this as a score 25. Finally, for the argumentation rhetoric, I already given an example, but here's another one from the data set, where we can see that one of the premises used by the argument, or the claim C, is referring to personal experience by saying, in my country, except for a minor part of professional athletes, well, and so on. So it's referring to personal experience, it's appealing to that, so we will annotate this argument with our argument rhetoric of ethos. So following these guidelines and following this rubric score, we effectively annotated 402 student persuasive essays, ending up with 1,908 arguments tagged, each one of them with all of the quality facets. We had 3 expert annotators, and of course we computed the inter-annotator agreement, which you can see in the table with kappa score, and all of them are fairly good, I would say, with a special attention to cogency, where here I put 5 labels and 3 labels, where 5 labels refer to the score from 0 to 25, but we also found during the annotation that it could be hard to annotate to separate the score of 10 and 15 and the score of 20 and 25. So maybe the granularity is too much in this case, in this scenario. So we also experimented with annotating with 3 labels. So we merged the labels of 10 and 15 and the labels of 20 and 25. And we see that the inter-annotator agreement improves, so it helps with the definition. Here are some quickly statistics. I lost my timer. Let me know if, okay. So here are some quick statistics on the dataset that we annotated. Mainly what I wanted to show here is, let's start with the left part, which refers to all of the rhetorical strategies annotated. I want to show that the majority of them didn't have any rhetoric structure, being almost 80% of them. And for cogency, which is in the blue color, we see that the distribution is more or so balanced between 0, 10, 15, 20, and 25. But for the reasonableness of rebuttal, so in yellow, we see that most of them, almost 80%, fall under the label of 0. The label of 0, if we go back to the table, refers to when the author introduces a counter-argument, but doesn't introduce a rebuttal. So to me, this was very strange, because if you introduce a counter-argument, usually you refute it, but it's the nature of the data set that we annotated that the students didn't introduce a rebuttal. So most of them fall under the score of 0, giving us a very unbalanced data set, and more so, the score of 0 signifies that there are no rebuttals. So that means that there were no text to learn from. So there were a counter-argument with no rebuttal pair. So that will impact in the results that I will show you later for the classification models. But first, before talking about how we build our models, I would like to give a quick introduction to embeddings. I'm pretty sure you're all familiar with it, but basically embeddings is a technique of obtaining a numerical representation of a piece of information. This can be a text, this can be a video, this can be an audio. But basically the main idea is to capture the semantic meaning of what we are being embedding. And in this example, I really like this graph, but as you can see, you could have the embedding of man and woman, and it will be intrinsically related to the embedding of king and queen. So you could operate, since they are vectors, and you could take the embedding of man, subtract king, and add queen, and you will end up somewhere around woman. So it holds all of these semantic meanings, relationships between the different words. Same here, you can see that all of the capitals are closer to the country names than to the others, and so on. But how do we use them? Well, first, we utilize different word embedding techniques, such as word-to-vec, GLOB, and also transformer-based embeddings to obtain the text embedding from the argument. So given the claims, the premises, we can extract the text and obtain a text embedding vector that represents the whole argument. But also, we can take advantage of the argument graph that we have. As you remember, we can construct an argument graph, such as so, where we have the claims and the premises. And this structured information is providing us valuable information, actually, that we can also utilize in our models. So we explore other techniques for obtaining graph embeddings, such as graph-to-vec, debug, and feeder G. In this work, we focus mainly on feeder G to obtain these graph embedding vectors. This this gives us the overview of the full architecture. Now I can actually explain the full model that we propose, where first we start with a persuasive essay, like I said, an essay written by a student, and we do two things. We first extract the graph from the argument, and using feeder G, which is at that moment was the state of the art for obtaining graph embeddings, we obtain a graph embedding vector representing that argument. And then from the text, we extract the text from the argument, and we utilize a transformer model. In this case, we utilize longformer, which is a model that works better with long text, and we obtain a text embedding vector. So then we can put the two together into a single feature vector and use it to feed a classifier such as an SVM. We experimented with many of them, but we feed it to a classifier to obtain a score for each one of the quality aspects. So in the end, we will have a final output that will look like cogency. The cogency of this argument is assessed as being 25, as the argument provides multiple reasons for the claim, and all of the reasons are sound, acceptable, and free of relevances. Now, for the argumentation rhetoric, you may be thinking that the argumentative, the argument graph part may be not that interesting, and you will be right. When we are trying to assess the argumentation rhetoric of a text, we are focusing on how the text is written and the content of the text. So we don't really care about if it's being supported by other premises, or if it's being attacked, or how many premises are being supported in this claim, etc. So we only focus on the text. So you will see in the results that when we add this graph aspect of the model, it doesn't really help to understand and to model the argumentation rhetoric classification. But we consider that there are other aspects that could help this, and this is what I put here as the emotion classifier. So we fine-tune a T5 model which is a transformer-based model, to basically do an emotion classification task. This will give us, given a text, a sentence, or a paragraph, this will give us a label that refers to the emotion used in this text. So this can be sad, this can be neutral, this can be happy, and so on. And then we can use this emotion label to obtain a word embedding and add it to the feature vector to be able to feed it to the classifier. So let's walk through the results one by one, and I will show you how this affects. Let me remove this. Okay. All right. So for cogency classification, as you can see here, well, I have an error here, but we experimented first with only long former embedding, so with only textual features, and we obtained different results. Like, for example, an F1 score of 0.74, or if you use an SVM as a score of 72. But when we start adding all of these graph features, we see an actual improvement on the F1 score, meaning that adding this structural information is actually helping the model to understand the cogency. Now, for reasonableness, we saw that the model is actually not showing a significant learner result, and this is the first part. And this is mainly due to the nature of the data set, where I said before that we do not have many rebuttals. Most of them were non-existent. So we didn't have enough information for be able for the model to actually learn something. So what we propose is a rule-based algorithm that basically applies all of the rules that we have in the table, in the rubric score, and we compute it for the rebuttal, and we see that we obtain an F1 score of 0.58. This, of course, should be improved with more data, and that's one of the future perspectives that we have for this thesis. Finally, for the rhetorics classification part, as you remember, we had most of them were non-rhetorical class, so we had a big imbalance in the data set. So we decided to go first to split the task into two parts. First, a binary classification in which we identify, which is represented by this table. It identifies if the sentence is rhetorical or non-rhetorical. So we put together ethos, logos, and pathos as a single label against all of the non-rhetoricals. And then we had a second step, which performs a multi-label classification between ethos, logos, and pathos. Finally, we obtain for the full pipeline, we obtain a 0.63 F1 score, showing that the model is actually able to learn. Also, I want to pinpoint here that what I said before, that when we add the graph embeddings here, which is represented by feeder G, we see that there are actually not improvements, actually adding noise to the model. But when we start adding the emotion embedding, it improves. And when finally we remove the graph and we keep only the textual and plus the emotion embedding, we obtain the better results. So to conclude this section of the presentation, we propose a novel annotated corpus of 402 essays with all of these quality labels. We were able to encode textual and graph structure jointly to better capture argument properties. We obtain a cogency score of 0.77, rhetoric for 0.63, and for reasonableness 0.54. And future work opportunities are in larger balanced corpora and in designing more domain-specific metrics that can be applied to each domain. All right. So how am I with time?
37.
What time we started?
At 5, so you have until 50.
Okay, great. So going to the next section. Now we want to see. Okay, now we were able to model some of the quality aspects for arguments, and now we want to see if we can do the same in the clinical domain, and so in the healthcare domain, specifically applied to the clinical medical text. So in this section, we will be addressing the last two big research questions of the thesis, which kind of adaptations are required to be able to assess clinical argumentation, and how we can integrate external knowledge to enrich the analysis of clinical decision. So the main motivation here is that in medicine, in healthcare, there exists a lot of black box models that lack transparency and are not really being trusted by doctors. In order to, for example, provide explanations for a clinical case or to decipher a diagnosis and so on. So particularly, we would like to focus on the medical, we focus on the medical resident students, so students that are finishing their medical studies, and they typically obtain, they get exercises to make where they have a clinical case and they need to explain why the patient has a certain diagnosis, for example. So they need to make these explanatory arguments in a way. The thing is that these explanatory arguments, these explanations require, they need to be verified. Since we are talking a very sensitive domain like healthcare, we cannot really claim something and that's it. We need to verify them with external knowledge, and it needs to be tailored to this specific clinical context. So the goals for this section are to be able to enhance explanations with structured knowledge validation, so to be able to obtain external knowledge and enhance explanations, to be able to do it in a transparent and data-driven way, but also to be able to assess the quality of these explanations, and we will talk about this in a minute, and how to promote to students a proper reasoning selection aligned with the medical expertise. So the approach that we take in this section is first to be able to understand the information that we can get in the medical domain. So we define this as the medical entities. There are different entities that you can introduce in your medical text, such as, for example, symptoms, studies results, age of the patient, location of if it has pain in the arm, and so on. And then to be able to align it to different medical ontologies. This is important because if we want to introduce the external knowledge, we need to be able to align the information that we find in raw text to the information that we have in the ontologies. Then we want to be able to transparently assess the explanatory power of reasons, meaning we want to assess all of these medical entities that we can find, which of them can explain better, for example, the diagnosis of a patient. And finally, we want to generate explanations using only the best symptoms or the best reasons that we can find in the text, and contrast them with other existing explanations. So a student, for example, may produce his own explanation, and our system may generate a different one and contrast it with the one that the student used by saying, okay, you should improve by using this reason and you should discard the other. We will see an example. First, I would like to introduce UMLS and HPO very quickly. UMLS and HPO are different resources. For UMLS, it's the Unified Medical Language System. It's a widely adopted resource that unifies the medical vocabularies, and it provides a semantic network that is giving a consistent categorization of the concepts. We draw from UMLS all of these categorizations in order to annotate our medical entities and in order to be in accordance with what the community uses in the medical domain. And then we utilize the Human Phenotype Ontology, HPO, which provides a list of diseases and associated terms, which are typically the symptoms of each one of the diseases, with extra information such as not only the definition and synonyms, but also the associated occurrences of these symptoms. So a symptom, let's say we talk about COVID, a symptom for COVID could be fever, and we can say the fever is very frequent for these symptoms. So they provide all of this annotation for each one of the symptoms, providing essential information that we can use to better explain the diagnosis. First, let's see what is the data set that we utilize for this work. The data set is composed of clinical questions, such as the one we have here, with a patient is being introduced with all of the symptoms, all of the possible symptoms that he has, all of the results that the laboratory studies had on the patient. And then we have a list of possible diagnoses that the patient could have, and the one involved is the correct one. So we know all this information. This is taken from exams for students, and the students, given the first part and the possible diagnosis, they have to argument and they have to create an explanation on why the patient in this case has thrombotic thrombocytopenic purpura. This dataset is composed of 314 unique clinical cases, and we annotated in such a way that we can have all of the different clinical entities, medical entities annotated. So for example, a 34-year-old falls under the categorization of age group. Again, all of these labels are taken from UMLS. Woman refers to the population group. Then we have, for example, fever and headache, which are a sign or a symptom that the patient may have, and so on and so on. So, something important that we have to remark here is that all of these terms may be written in what we call layman terms. So they're not written in the exact term that the ontology may have. And that's what shows us the need of aligning, to be able to align all of these entities that we find in the text to the ontologies. It's not that we can just search for it, but we need to provide a smart way of doing that. So this is a bit of the statistic. I will go through quickly through this, but basically we annotated 4,845 entities, and we obtained a reasonable agreement among all of the annotators. But more importantly, since we were part of the annotators and we are not doctors, we need to validate all these annotations, and we perform a validation from a medical perspective with the doctor. We gave a random sample of 30 cases, which was roughly the 10% of the data set. And he basically went through all of the annotations and validated by saying, okay, this is good, this is bad, this is lacking a word, this is having an extra word, and so on. But in the end, the results show that 98% of the data was labeled correctly, which in a way validates our data set. So to show you first the pipeline that we propose, we start from a clinical case. So again, we have all this information about the patient, all of the diagnosis, the correct diagnosis, and all of the possible diagnoses. And then we first extract the text, and we will do the medical entity recognition. Here is mentioned as symptom detection, but what we are doing here is detecting all of these medical entities that we annotated before. And then we keep only the list of symptoms. Also, for each one of the diagnoses, we query HPO, so we query the ontology, and we obtain the related information for each one of the diagnoses, such as all of the symptoms that are found in them and the frequencies for each one of them. So the two of them, the list of symptoms and the symptoms found in the possible diagnosis, are fed into what we call the symptom matching module, which basically aligns all of the symptoms that we found in the clinical case with the symptoms that are found in HPO. Here is saying match, being that it found it there, or not match, meaning that it didn't found it. For the generated explanation, I will leave it for before. I would like to first tackle each one of the parts. So for the medical entity recognition, we propose basically a token classification model. Given all these labels, we want to identify and classify all these medical entities. And we experimented with different large language models specialized in biomedical domain, with the best results obtained with Shivert and Cased, and we see that we have an F1 score of 0.86 for all of the labels. And here we have the specific results for each one of the entities. And since we are using the symptoms, if we check here, we see that for sign of symptom, we obtain an F1 score of 0.82, which in comparison to similar works, which by Nye in 2022, they obtain an F1 score of 0.61. So we see that our model is not only able to learn, but is also performing better than what is the state of the art. So then going to the symptom matching model, the idea here is to be, as I said, is to be able to find a symptom and match it to the one in HPO. So this is a screenshot from the ontology for fever. So you see it has its own ID, it has the synonyms, as I said, it has some definitions, but also it has all of the related diseases. So all of the diseases that have fever as a symptom. And how do we do this symptom matching? Well, we propose to use contextual embeddings in order to identify the best, to identify, to align the symptoms. How do we do this? I will do it straight with the example. So let's say we detected the symptom confused in this sentence, in the text. So she's confused and oriented only to person. What we propose is a methodology where we extract the symptom, being confused, and we compute the embedding by using different embedding techniques. We compute the embedding of confused, but we also take into account the full context of the symptom in which was found. So the full sentence, she is an oriented to person. So the full sentence without the symptoms, and we compute the embedding for it too. So then we can sum them, and we can compare against the same methodology, but to all of the HPO terms that we find in the ontology. So this means that we are taking the same context for each one of them, but we are changing each one of the terms, each one of the possible terms in HPO. By doing this, we then compute the cosine similarity and keep the top one, meaning that is the one that matches the closest one in the context to confused, say. So this methodology of matching symptoms to an ontology with the use of the context is something new, at least with HPO and with medical ontologies. There is one system which is called DASH, proposed by Enrico, and what they propose is they do not use the context, and they propose a system in which you just type in layman terms a symptom, and it will find you the closest one in HPO. So we use it to test against ours, and we see that we have the different models with the context and without the context. So for DASH, they obtain an accuracy of 0.37. And when we use our best model without the context, we see that we have something fairly similar, so 0.41. But when we add the context, we jump a bit to 0.53 of accuracies, showing that the adding of the context is actually important to be able to align all of these symptoms. So now, going a bit back to the argumentation quality part of the work, we mentioned something called reason assessment. So by reasons, I mean when someone has to explain, so an explanation can be seen as an argument, of course, and when someone has to explain a situation or has to explain something, it selects reasons. You select different reasons to use to be able to explain. So I will show you an example. Let's say that John drives his car to work every day, taking the same route. But today he decided to take a different one and got into a car accident. If I ask you why John got into a car accident, most of the people will think because he took a different route. So what you've done there is an internal reason selection method where among all of the possible reasons, you selected the one that helps to explain better the situation. And when I say all of the possible reasons, I'm saying that it could also be that, for example, someone, he didn't sleep well, so he was sleepy, or that someone was drunk driving and crashed on him. So there are infinite possible reasons to explain everything. And typically we do not use all of them, and we are not exhaustive, or at least if you want to have a good explanation, we do not do that. We do this reason selection methodology to provide a good explanation, a simpler explanation, let's say. So I went to social studies, to philosophy and psychology, and I found that this is actually being studied. There are different biases that people rely to do this, such as abnormality. So in this case, the abnormality will be that the John took a different route, so that's abnormal, so that conditions your explanation. But it could also be contrasting or simplicity. So the idea that I propose in this contribution is that to be able to propose a methodology to be able to model this reason selection applied to the medical domain, and by using all this external information we can find in HPO. So here's what I said applies specifically to the medical domain. So we introduce something called prevalence function, which basically assesses the pertinence of all of these reasons. By reasons in this case, we are talking about symptoms. So we evaluate them based on different information that we can find on HPO and information that we can find in the clinical text. First, if, for example, the symptom that we found in the clinical text that the patient has is, for example, a symptom of the correct diagnosis. So that gives us information to be able to explain. Then you can also have the occurrence rate, the uniqueness of the symptom, the presence of it in the clinical case, and so on. So this provides us a way to assess all of these reasons grounded in external knowledge. And what we propose is a transparent deterministic algorithm that can actually be able to explain why you chose those reasons and to be able to suggest students the reasoning logic that they should be taking. So here I have an example for two small symptoms, thrombocytopenia and stiff neck, and you see that what we do is basically check all of these features for each one of the symptoms and see if they're true or false, and then based on these features, the algorithm will score each one of the reasons, saying, okay, this is very pertinent and this is not very pertinent. So now what do we do with that? Okay, so we can use the high scored reasons, but unused, for example, if the student provides an explanation that didn't use a high scored reason, we can use it and say, okay, you have this gap here and you should consider, for example, in this example, you should consider invoking thrombocytopenia, since it's a system that is, for example, unique to the correct diagnosis, has a high occurrence rate, and is present in the clinical case. This enables us then to propose suggestions to the students, but not only adding the high score, but also to suggest to remove low score entities. And we generate these explanations first with template-based explanations, but you could also explore, like in the new generative AI, which is future work, and I will show a bit of that, in order to generate all of these explanations. So to conclude this section, what we propose is a specialized pipeline that extracts and aligns all these clinical entities from medical text and aligns them with ontologies. We used contextual embedding to map all of these terms. We propose a transparent function that is inspired by cognitive science that can assess all of these reasons. And it's basically providing us with a systematic assessment of the medical explanation quality. I will show a demo. I have a demo for this, so maybe it will be easier to understand. This is a small system that I built for the sake of the presentation. It's not even published yet, but we'll see. But basically, what you can do is introduce a clinical case. As I said, your input will be a clinical case. Then you say what are the diseases that are in play here, so the correct disease and all of the other possible diseases. And the system then will go, first we'll run a name entity recognition system to show you all of the entities that can be found in this clinical case, such as age group, I don't know, fever, sign of symptoms like fever and headache. So it's the same example that I showed before, but this is being run by the model. And finally, it will rank all these reasons that it will find, and it will generate an explanation based on that. So this one is using ChatGPT, version 3, I don't remember, but maybe I should put it in bold for the next time, but it says that one of the key reasons for considering the correct answer is the absence of symptoms such as nuchal rigidity, fever, increased CSF protein concentration, blah, 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 and says that these symptoms are commonly associated with the other possible answer, but they are not found. So since you didn't find all of these symptoms, you can discard meningococcal meningitis. Well, it's saying it here. So the idea is to provide the system all of these ranked list of reasons, and then generate all of these explanations. So I will show you. Let's see if it works. I have to share I have to change the screen. Well, maybe I won't do it. I will think of a better solution for next time. But it will work as I show here before. So for the conclusions of the presentation, all of the research contributions goes as follow. First, we annotated a persuasive essay corpus for quality research, which is a domain with very few data sets, so it's a very interesting resource. We propose novel techniques to model different quality attributes like cogency, rhetoric, and reasonableness by utilizing combining textual, graphical, and emotional features. We propose a specialized medical pipeline to extract, align, and assess clinical entities, which is grounded in external ontologies, take into account that this methodology could also be applied to different domains in which you have ontologies on your own domains. So by defining your own prevalence function, you could assess reasons with the information extracted from other domains ontologies. And I showcase some proof of concept applications that I couldn't show the link, but I have the screenshots. All of this work derived in multiple publications among many of you here. That's all for me. And I'm lost with the time, so.